In the golden afternoon light of a summer meadow, something remarkable is happening. A single honeybee returns to her hive after discovering a patch of wildflowers blooming half a mile away. Within minutes, dozens of her sisters will fly directly to that exact location, navigating through forests and over hills they've never seen before. They won't follow her. They won't track her scent. Instead, they'll decode a message she delivers through movement alone. A message so precise, it includes distance, direction, and even the quality of what awaits them. This is not instinct. This is language. Honeybees possess one of the most sophisticated communication systems in the animal kingdom, rivaling the complexity of primate gestures and birdsong. Yet for thousands of years, humans watched bees dance inside their hives without understanding what they were witnessing. The movements seemed chaotic, purposeless. It wasn't until the mid-20th century that researchers began to realize these weren't random motions at all. They were instructions. A forager bee who has located a valuable food source doesn't simply return and hope others will stumble upon it. She performs a behavior that has been refined over millions of years of evolution, the waggle dance. On the vertical surface of the honeycomb, surrounded by her sisters, she walks in a figure-8 pattern, waggling her abdomen during the straight portion of the path. To the untrained eye, it looks like restless energy. But every element of this dance is encoded with information. The angle of her waggle run, relative to vertical, corresponds to the angle between the sun, the hive, and the food source. If she waggles straight upward, the flowers are in the direction of the sun. If she waggles 45 degrees to the right of vertical, her sisters must fly 45 degrees to the right of the sun's position. This is geometric communication, using the hive itself as a reference frame and the sun as a compass. The bee translates three-dimensional space into a two-dimensional map that can be read in the darkness of the hive, where vision is nearly useless. But direction is only part of the message. The duration of the waggle run communicates distance. A brief waggle lasting less than a second indicates a food source just a few hundred meters away. A longer waggle, sustained for several seconds, tells the recruits they'll need to fly a kilometer or more. Studies have shown that bees can communicate distances up to 6 miles with measurable accuracy, adjusting their dance tempo based on the effort required to reach the destination. There's even more embedded in the performance. The vigor of the dance, the intensity of the waggling, and the number of repetitions signals quality. A bee who has discovered an abundant patch of nectar-rich flowers will dance with enthusiasm, repeating the pattern dozens of times. A less impressive find might warrant only a few half-hearted circuits. This allows the colony to allocate its foraging force efficiently, sending more workers to the richest sources and fewer to marginal ones. Researchers have tested this system with astonishing rigor. By training bees to feeders placed at known distances and directions, then observing the dances they perform upon returning, scientists confirmed that the language is consistent, learnable, and translatable. In some experiments, robotic bees were constructed to perform dances inside observation hives. When the robots executed the correct waggle angles and durations, real bees followed their instructions and flew to the predicted locations. The code had been cracked. But the waggle dance is not the only signal bees use. When a forager finds a food source very close to the hive within about 50 meters, she performs a different dance called the round dance. She moves in tight circles, alternating directions, without the waggling motion. This tells her nestmates that food is nearby, though it doesn't specify direction. The assumption, built into the behavior, is that something so close can be found through local search and scent cues. Sound also plays a role. During the waggle dance, the bee produces vibrations with her wings, creating a low-frequency buzz that can be felt by bees in close contact with her. This acoustic element may enhance the signal, helping recruits follow the dancer more closely in the crowded, dark interior of the hive. Some evidence suggests these sounds also convey additional information, though researchers are still working to understand the full complexity. Scent is woven into the communication as well. The dancer carries the fragrance of the flowers on her body, and she may release pheromones that prime her sisters to search for that specific aroma when they arrive at the coordinates she's described. This combination of spatial information and sensory cues creates a multi-layered message that is both abstract and concrete. What makes this system even more remarkable is its flexibility. Bees adjust their dances based on environmental conditions. On cloudy days, when the sun is obscured, they can still navigate using polarized light patterns in the sky, and their dances reflect this. If the colony is under stress or resources are scarce, the threshold for what constitutes a good food source shifts, and dances become more or less frequent accordingly. The language is not rigid, it adapts. This communication isn't limited to food. Scout bees searching for a new nest site during swarming use the same waggle dance to advertise potential locations. Different scouts may promote different sites, and the colony makes a collective decision based on the enthusiasm and persistence of the dances. The site that generates the strongest and longest-lasting dances wins. This is democracy through dance, a decentralized decision-making process that emerges from individual signals. Understanding this hidden language has profound implications. Honeybees are among the world's most important pollinators, contributing to the reproduction of wild plants and the production of crops that feed billions of people. Their ability to communicate allows a colony to function as a superorganism, deploying thousands of workers with precision across vast landscapes. When that communication breaks down due to pesticides, habitat loss, or disease, the entire colony suffers. Scientists have observed that certain pesticides interfere with the waggle dance. Bees exposed to sublethal doses of neonicotinoids, a class of insecticides, perform dances that are less accurate, shorter in duration, or abandoned altogether. The bees can still fly, but they struggle to translate what they've learned into the language their sisters understand. The result is a colony that becomes disoriented, less efficient, and ultimately weaker. Researchers continue to explore the nuances of bee communication, uncovering new layers of meaning in behaviors that once seemed simple. Some studies suggest that bees may communicate information about predators or threats, using specific signals to warn the colony. Others are investigating whether bees can share information about the availability of water or resin, both of which are critical resources. The waggle dance is not unique to honeybees, though it reaches its highest expression in their species. Some closely related bees perform simplified versions, and other social insects use pheromone trails or acoustic signals to coordinate group behavior. But the honeybee's system stands out for its abstraction. It is a symbolic language, one that represents the world through geometry and movement rather than direct sensory experience. This capacity challenges long-held assumptions about the limits of insect cognition. For decades, insects were viewed as simple automatons, driven by hardwired instincts with little room for learning or flexibility. The waggle dance reveals something different, a communication system that requires memory, spatial reasoning, and the ability to translate sensory input into abstract symbols. A foraging bee must remember the route she flew, calculate the angle relative to the sun's position, and encode that information into a dance that others can interpret. This is not automation, this is processing. In the dim, humming interior of a hive, surrounded by thousands of her sisters, a single bee completes her dance and pauses. Around her, recruits touch her with their antennae, absorbing the message she has delivered. One by one, they leave the hive, their flight paths aligned with invisible coordinates described in motion and vibration. They will find the flowers. They will return with pollen and nectar. The colony will thrive. And all of it unfolds through a language humans are only beginning to understand. A hidden code, written not in words or sound, but in the precise, purposeful movements of bodies that have been speaking to one another for millions of years.